Tonight, we're going to dismantle a picture of the universe that's been sitting quietly in your mind since you were a child, so familiar you've probably never once questioned it. You know the picture. Space stretching out flat and endless in every direction, like a grid of graph paper with no edges, scrolling on forever past the planets, past the stars, past everything you've ever read about in a textbook. It's the picture behind every star map you've seen, every diagram of the solar system, every illustration of the universe, tucked into the back pages of a science book. And it feels obvious. It feels like the only way space could possibly be. But here is the question that should keep you up tonight, if you let it sink in. If gravity bends space, and we know it does, we've measured it, we've watched starlight curve around the edge of the sun, then why doesn't the universe as a whole bend back on itself the way a sphere does? Why isn't space curved like the surface of a ball, or warped like a saddle instead of running on flat forever? It sounds like a small geometry question. It is not. It is one of the strangest, most unresolved tensions in modern cosmology, and the answer, or the lack of one, touches something most people never imagine: the actual fate of everything that exists. What we're about to walk through tonight is larger and stranger than most people ever imagine. It involves a number so finely balanced that physicists call the alternative a crisis. It involves a satellite that briefly suggested the universe might be curved after all, and then, on a second look, took it back. And it involves a mystery sitting in data gathered just in the last 2 years. A mystery that might mean the very thing we call dark energy is something else entirely, something tangled up with the shape of space itself. We are not going to answer this cleanly tonight. Nobody can yet, but we are going to get closer to the edge of what's known than you've likely ever stood before. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now let's begin. Think back for a moment to the very first time someone tried to show you the universe. Maybe it was a poster on a classroom wall, or a page in a science book, or a planetarium ceiling lit up with painted stars. Whatever it was, there's a good chance it handed you geometry without ever telling you it was doing so. It gave you flat space and let you assume that's simply what space is. So here's a question worth sitting with before we go any further tonight. What shape did you picture the universe as back then, as a child? And have you ever actually stopped since to ask yourself whether that picture was even right? Hold on to that question, because we're about to take that flat, comfortable, familiar grid apart, piece by piece, and show you what it's quietly been hiding. Let's start with the grid itself, because almost nobody questions where it came from. The flat, infinite version of space you carry in your head, 3 directions, stretching out forever, intersecting at perfect right angles. That picture has a name. It's called Euclidean space, after a Greek mathematician who lived more than 2,000 years ago and never once looked through a telescope. Euclid wasn't describing the universe. He was describing a floor, a wall, a flat surface you could draw on with a straight edge. And somehow, that floor became our default assumption for the shape of everything that exists. For most of human history, nobody had a reason to doubt it. Space seemed obviously, self-evidently flat, the same way the ground beneath your feet seems obviously flat, even though you are, in fact, standing on the surface of a curved sphere nearly 13,000 kilometers across. That's worth sitting with for a second. You have spent your entire life on a curved surface that feels completely flat to you because you are too small, standing in too small a patch of it to notice the curve. Hold that thought. We're going to come back to it. Then, in the early 20th century, a patent clerk in Switzerland looked at the question differently than anyone before him and broke the floor open. Albert Einstein didn't just ask what shape space is. He asked something stranger. What if space isn't a fixed, rigid stage that things happen on top of? What if space itself can bend, stretch, and warp, depending on what's inside it? His theory of general relativity, published in 1915, made a claim that still sounds almost like science fiction the first time you hear it stated plainly. Mass and energy don't just sit inside space, they reshape it. A star doesn't simply occupy a point in space. It dents the space around it, the way a bowling ball dents a stretched sheet of fabric. And anything moving nearby, including light itself, follows the curve of that dent, not a straight line through some imaginary flat backdrop. We've confirmed this, by the way, not just on paper. In 1919, astronomers watched starlight bend as it passed near the edge of the sun during a total solar eclipse, exactly the amount Einstein's equations predicted. Light, the straightest traveling thing in the universe, curved. Space had teeth. Space had shape. So now here is the real question, the one that was hiding underneath the first one. If a single star can curve the space around it, what happens when you stop looking at one star and start looking at everything? All the matter, all the energy, every galaxy, every cloud of dark matter, every last erg of energy in the cosmos, all at once. What shape does that make? Does the universe, taken as a whole, curve back on itself? Does it warp the other way? Or does all of that mass and energy somehow cancel out, leaving space lying flat after all, the way you assumed all along? General relativity gives us exactly 3 possible answers. Not 4, not a spectrum of infinite options, 3 distinct geometries, and the universe has to be one of them. The first is what cosmologists call a closed universe. Picture, if you will, the surface of a sphere, not the inside of a ball, not a solid globe, but the curved 2-dimensional skin stretched around it. Only now imagine that same kind of curvature applied to all 3 dimensions of space at once. In a closed universe, if you drew 2 parallel lines and let them travel far enough, they would eventually bend toward each other and meet the same way 2 ships sailing due north from different points on Earth's equator will eventually converge at the North Pole, even though they never once turned. In a closed universe, a triangle's 3 angles add up to more than 180 degrees. And if you traveled in a perfectly straight line, long enough, in one direction, you would eventually come back around to where you started, having circled the entire universe like a coin tossed off the surface of the Earth, returning to your own hand from the opposite side. The second possibility is the open universe, and you should picture this one as the surface of a saddle or the bell of a trumpet, curving outward and away from itself in every direction. In an open universe, parallel lines don't converge. They drift apart slowly the farther they travel. A triangle's angles add up to less than 180 degrees. Space here isn't bending back on itself at all. It's spreading, opening like a sheet of rubber stretched faster at its edges than at its center, with no boundary and no way to ever circle back to your starting point. And the third possibility, the one we were both handed as children without anyone telling us, it was a possibility rather than a fact, is the flat universe. True Euclidean space, where parallel lines stay parallel forever, where a triangle's angles add up to exactly 180 degrees, and where space simply runs on uncurved in every direction without ever folding back or peeling away. 3 geometries, 3 entirely different cosmic destinies, by the way, not just 3 different diagrams. We'll get to that. And the strange part, the part most people never learn, is that nothing about the laws of physics demands that we live in the third one. There is no rule of nature that says, the universe shall be flat. Flatness isn't the default setting. It isn't the simplest option chosen automatically by some cosmic Occam's razor. It is one specific, narrow outcome, sitting precisely between 2 much larger families of possibility, sitting on a dial that could, in principle, have landed almost anywhere. So what decides which one we actually got? It comes down to something cosmologists call critical density. Essentially, the average amount of matter and energy packed into every cubic meter of the universe. Too much density packed into the cosmos and gravity wins. Space curves back on itself, closed like that sphere. Too little density, and space wins the tug-of-war the other way. It opens outward forever like that saddle. And only one extremely specific density, neither too much nor too little, but exactly enough, leaves you with the flat, familiar grid you grew up picturing. Think about that for a moment. Somewhere out there, encoded in the actual physical contents of the universe, in how much matter exists, how much dark matter, how much dark energy, how much of everything, added up across all of space, there is a number. And that number, whatever it turns out to be, determines whether you live inside a sphere, a saddle, or a sheet of flat, endless graph paper. It is not a guess. It is not philosophy. It is measurable, and it has been measured. We'll get to exactly what that measurement found, and why the answer it gave back made physicists more uneasy than relieved. That's coming. But before we go there, I want you to actually sit with the 3 shapes we just laid out, because most people glance past them without ever picturing them properly. So, if you found out tomorrow with absolute certainty that space curved back on itself like the inside of a sphere, that if you traveled far enough in a straight line in any direction, you'd eventually circle back to where you started, would that feel comforting to you, like a universe with a kind of built-in wholeness? Or would it feel suffocating, like discovering the walls of a room you always thought was open-ended? Sit with that, because the measurement we're about to walk through didn't just tell physicists which of these 3 shapes we live in. It told them something far stranger. It told them how close we came to the edge of all 3 at once, balanced on a margin so thin that the people who first calculated it didn't quite believe their own numbers. So how do you actually measure the shape of something as large as everything? You can't step outside the universe and look at it from above, the way you might look down at a curved soccer ball resting in your palm. There is no above to stand on. And yet, astonishingly, there is a way to measure it from the inside, and it comes down to that one number we mentioned a moment ago: density. Here's the logic, and it's simpler than it sounds. Picture the entire universe as a kind of cosmic recipe, with a fixed amount of matter, and dark energy mixed into a fixed volume of expanding space. There exists one very specific average density. Cosmologists call it the critical density, that would leave space perfectly flat. It works out to something almost laughably small, somewhere around 5 or 6 hydrogen atoms in a volume the size of a phone booth, smeared out evenly across all of space. Not 5 atoms in a room. 5 atoms in a box you could stand inside, repeated, on average everywhere, for billions of light years in every direction. That is how empty the universe actually is, and that emptiness, that precise thinness, is the dividing line between three entirely different cosmic fates. If the actual density of everything in the universe is higher than that critical value, gravity wins the long game, and space curves back on itself, closed, like the sphere we described a moment ago. If the density is lower, space loses that battle and keeps opening outward forever, the saddle shape, expanding without end. And if the density lands exactly on that critical value, not too much, not too little, but exactly enough, you get flat space. The grid, the graph paper, the picture you grew up with. Cosmologists give this ratio a single letter, omega, written as the Greek symbol omega. Omega equal to 1 means flat. Omega greater than 1 means closed. Omega less than 1 means open. It is, quite literally, the dial that decides the shape of everything. And unlike almost every other number in physics, this one didn't have to land where it did. So they measured it. And the way they measured it is one of the most elegant tricks in modern science. Here's how. Roughly 380,000 years after the Big Bang, the universe cooled enough for light to finally travel freely instead of scattering endlessly off charged particles, the way fog scatters a headlight beam. That moment left behind a faint afterglow that still fills the sky today, in every direction, called the cosmic microwave background. The oldest light there is 18 billion times fainter than starlight, a fossil radiation from when the universe was an infant. Within that ancient glow are tiny temperature ripples, frozen patterns from sound waves that rippled through the hot early universe, each one stamped at almost exactly the same physical size when the light was released. And here is the elegant part. Because we know the true physical size of those ripples, and because light traveling toward us through curved space bends differently than light traveling through flat space, the apparent angular size of those ripples in our sky becomes a ruler. A ruler that tells us, indirectly but powerfully, whether the space the light traveled through to reach us is curved or flat. In 2018, after years of painstaking analysis, the Planck satellite team announced their result, combining the cosmic microwave background data with independent measurements from how galaxies cluster across the universe. The number they landed on for the curvature, omega-1, came out to 0.7 with an uncertainty of 0.19. In plain language, flat to within about 0.2%, not approximately flat, not roughly flat. Flat to a precision most people would assume was impossible to even ask the universe about, let alone answer. Remember that flat diagram you grew up with, the one sitting in the back of a textbook somewhere in your memory. It turns out it wasn't lying to you. Space really does appear to run flat, in every direction we can measure, with a confidence that would satisfy almost any other branch of science. And that is exactly where the real unease begins. Here's the part almost nobody tells you, the part that turns this from a tidy confirmation into what physicists actually call, with no exaggeration, the flatness problem. Flatness, omega equal to exactly 1, is not a stable resting point for the universe. It is the opposite. It is what's called an unstable equilibrium, the cosmic equivalent of balancing a pencil perfectly upright on its tip. Nudge it even slightly toward closed, and over billions of years of cosmic expansion, that nudge doesn't fade away, it grows, compounding, pulling the universe further and further from flat, the same way a tightrope walker who leans even 1 degree off balance doesn't stay at 1 degree forever. They keep tilting, faster and faster until they fall. The universe has had 13.8 billion years to fall off that edge in one direction or the other, and it hasn't. It is still standing there, balanced, almost exactly on the pin. So physicists ran the numbers backward, asking what the universe's density would have needed to be at its very earliest moments to still look this flat today, after all that time, after all that expansion. And the answer, when you trace it all the way back to what's called the Planck time, a sliver of a second so brief it has 43 zeros after the decimal point, is almost impossible to say out loud without it sounding like an exaggeration. At that moment, omega would have needed to equal 1 not to 1 decimal place, not to 10, but to roughly the 60th decimal place. One part in a number so large it dwarfs the count of atoms in your entire body, in your house, in the planet beneath your feet. Tuned, precisely, for no reason anyone could yet explain. That is the crack. Not that the universe turned out flat, that on its own would be a clean, satisfying answer. The crack is that flat, mathematically, is the single hardest outcome to land on by chance. And somehow, against every expectation drawn from the raw physics of an expanding universe, that is exactly where we are standing. So here's something worth sitting with for a moment. The same way you sat with the image of the universe you carried as a child. Knowing now that flatness isn't the easy, default answer, that it's actually the most improbable, most delicately balanced outcome of the three, does that change how you feel about it? Does it feel more unsettling to you that the universe might have been curved, closed in on itself, or flung open forever? Or does it feel more unsettling that it landed, against the odds, on the one outcome requiring this much impossible precision? Hold that feeling. Because the explanation cosmologists eventually arrived at for this knife's-edge balance required rewriting our entire understanding of the universe's first fraction of a second. An idea so strange that it didn't just solve the flatness problem, it nearly solved it too well, leaving behind questions we are even now, in the last 2 years, still fighting to untangle. So how do you tune something to one part in a number with 60 digits without an explanation that sounds like sheer, impossible luck? For decades, that question sat largely unanswered, a footnote of unease tucked inside an otherwise successful theory. Then in 1980, a young physicist named Alan Guth, working at MIT, proposed something that sounded at the time almost reckless. What if the early universe didn't simply expand the way it does today, gradually, steadily, the way it's been measured expanding ever since? What if instead, in its first unimaginably brief instant, the universe underwent a burst of expansion so violent, so exponential, that it makes today's expansion look almost motionless by comparison? This is the idea now known as cosmic inflation, and it remains to this day one of the most important and most actively debated proposals in all of cosmology. The picture it paints goes something like this. In a sliver of time so small it's measured in fractions of a second with dozens of zeros after the decimal point, a strange field of energy, sometimes called the inflaton field, drove space to double in size, and then double again, and then again, repeating that doubling roughly 60 times over before switching off. 60 doublings doesn't sound dramatic until you actually do the multiplication. It means a patch of space smaller than a single proton, in less time than it takes light to cross an atom, ballooned outward to become larger than the entire visible universe you can observe tonight, looking up. Let that sink in for a moment. Everything you can see, Every star, every galaxy, the most distant light astronomers have ever detected, all of it, by this account, was once compressed into a region smaller than the period at the end of a sentence. Now here's why this matters for flatness, and the analogy almost every cosmologist reaches for, because it genuinely is the clearest way to picture it. Imagine an underinflated balloon, deflated and wrinkled, its rubber surface covered in folds, creases, dents, all the small, uneven curvature a flat, taut balloon shouldn't have. Now imagine inflating that balloon not gently, but violently, blowing it up to the size of a house in a fraction of a second. What happens to the wrinkles? They don't disappear, technically. They're still there mathematically, somewhere on the surface. But they get stretched so far apart, so thin, that any small patch of that balloon's surface, say, the patch the size of your hand, now looks essentially flat. Not because the balloon became flat everywhere. Because the curvature, whatever it originally was, got stretched out past the point where a small observer, standing on a small patch, could ever detect it. That, in essence, is what cosmic inflation did to space itself. Whatever curvature the universe started with closed open. Wildly uneven, inflation stretched it out across a volume so enormous that the small patch we call the observable universe, the one we can actually measure, now looks flat to a precision of 1 part in many thousands. Simply because we are standing on an infinitesimally small corner of something vastly larger. Remember the earlier thought we asked you to hold on to, about standing on the curved surface of the Earth and it feeling flat beneath your feet because you're too small to notice the curve. Inflation is that idea, but turned up to a scale that barely fits inside language. We're not standing on a planet that merely feels flat. We may be standing in a patch of universe so small relative to the whole that it would feel flat even if the true, total universe curves back on itself, somewhere far beyond anything we could ever travel to or observe. Inflation, in other words, doesn't just explain why the universe is flat. It suggests the universe might not be flat at all, not really, not totally, and that what we're measuring as flatness is simply the local appearance of something we are far too small and far too young to see the true shape of. We're going to come back to that thought later tonight, because it changes everything about what the shape of the universe even means. But for now, hold on to this. Inflation solved the flatness problem not by making the universe flat, but by making it large enough that flatness became the only thing a small observer like us could ever detect. And the evidence for this isn't only theoretical. Inflation also predicted something specific and testable, that the tiny quantum fluctuations rippling through that almost unimaginably small patch of pre-inflationary space would get stretched out, alongside everything else, into the seeds of all future structure. Every galaxy, every cluster, every vast cosmic filament of matter stretched across hundreds of millions of light years. All of it, by this account, began as a quantum flicker, smaller than an atom, magnified by inflation into the blueprint for the entire visible cosmos. The satellites that first mapped the cosmic microwave background in detail, COBE in the early 1990s, then WMAP in the 2000s, then Planck after that, found exactly the kind of fluctuation pattern this theory predicted. Not proof. In the absolute sense, science rarely deals in proof, but confirmation, layer after layer, of a theory that started as one physicist's strange idea about a runaway balloon. So the flatness problem found its resolution, or at least its leading explanation. Case closed, you might assume. And for a while, most cosmologists treated it more or less that way. But that is only the beginning of this part of the story, because in the last several years, the ground actually shifted beneath this tidy resolution, and it shifted in a way that almost nobody outside the field heard about. When the Planck satellite team released their third major round of results in 2018, using one particular method of processing the raw data, a pipeline known among cosmologists by the name PLIC, something unexpected came back from the cosmic microwave background data on its own, before it was combined with any outside measurements. Instead of confirming flatness, that dataset, used alone, leaned toward a closed universe. Omega-1 came out around -0.44, with the uncertainty band not quite reaching all the way to zero. Statistically, this wasn't an overwhelming result, but it was enough to unsettle people enough that several serious papers published not by fringe researchers, but by working cosmologists argued openly that perhaps the simplest, most boring assumption, flatness, might be wrong, and that the universe might genuinely be closed, gently curving back on itself like that sphere we described earlier, just at a radius so vast, it would take longer than the age of the universe to notice the curve directly. For a few years, this became a real, open question inside cosmology, not dramatic enough to make headlines, but serious enough that conferences debated it, and grant proposals were written to resolve it. Some called it, with a flicker of dark humor, the Planck closed universe crisis. Then, more recent reanalysis of the same raw Planck data, using an updated processing method called PR4, with improved corrections for instrumental effects the earlier pipeline hadn't fully accounted for, brought the number back towards zero. The newest figures put Omega-1 at roughly -0.12, with an uncertainty of about 0.10. Consistent with a flat universe, the apparent lean toward closed essentially evaporating once the data was cleaned up more carefully. The crisis, it turned out, may have been less a crisis in the universe, and more a crisis in how a particular instrument's quirks were being handled. We tell you this not to bury you in statistics, but because of what it reveals about the nature of this whole inquiry. Even the experts, working with humanity's most precise instrument for peering into the structure of the cosmos, briefly thought they'd found a curved universe, and then walked it back. This is not a story of scientists who don't know what they're doing. It is a story of how close to the edge of detectability this question actually sits. How a problem that seems, in principle, simple, is it flat, or isn't it, turns out to require squeezing every last drop of precision out of instruments built at the very limits of what physics allows us to build. There is no ceiling on how careful you have to be to answer this question. There is no shortcut. There is no wall you can lean on and call the matter settled forever. Each new generation of data, each refinement of analysis, peels back another layer of uncertainty, and the flatness of the universe remains, even now, a live, breathing question rather than a closed book. So here's something worth asking yourself, the same way you asked yourself, a little while ago, what shape you imagined the universe to be as a child. Knowing now that the very people whose entire careers are built on measuring the universe's shape briefly thought they'd found something different than flat, and then had to quietly revise that conclusion once they understood their own instrument better. Does that make you trust the final answer more, because it survived that kind of scrutiny? Or does it make you trust it less, knowing how easily a number this delicate can wobble depending on exactly how you process the light? Whatever you decided just now, hold on to it loosely, because the story doesn't end with Planck, and it doesn't end with the cosmic microwave background at all. In just the last 2 years, an entirely different instrument looking at an entirely different kind of light, mapping 14 million galaxies scattered across billions of light years, found something that has reopened this question in a way nobody fully anticipated. A finding so strange that some cosmologists now wonder whether the thing we've been calling dark energy all along might actually be the universe's curvature, wearing a disguise we hadn't thought to look for. That is where we're going next, and it is, without exaggeration, the part of this story where the scale of everything we've discussed so far is about to look small. Everything we've described so far, the balloon, the wrinkles, the tightrope walker frozen mid-fall, all of it was built on cosmic microwave background light, the oldest light there is, captured by satellites looking almost straight back to the beginning of time. But there is a second way to measure the shape of the universe, one that doesn't look at the universe as an infant. It looks at the universe as it stands now, full of grown galaxies, scattered across billions of years of cosmic history. And in just the last 2 years, that second method has handed cosmologists a result so unsettling that some of them are still arguing, in papers published only months ago, about what it actually means. Here's how this second method works, and it's almost as elegant as the first. Back when the universe was still hot, dense plasma, before that 380,000-year mark when light finally broke free, sound waves rippled through it, the same way sound ripples through air, compressing and decompressing matter as they traveled. When the universe cooled and that plasma turned transparent, those sound waves froze in place like a photograph taken mid-ripple, leaving behind a subtle pattern. Galaxies, when they later formed, became very slightly more likely to cluster at one particular distance from each other, roughly 480 million light-years apart, give or take. Astronomers call this pattern baryon acoustic oscillation, and because we know from the physics of the early universe almost exactly how large that distance should be, it becomes a second cosmic ruler, one stamped not into ancient light, but into the actual arrangement of galaxies themselves, scattered across the sky like a fingerprint of sound frozen at the dawn of time. If you can measure how large that ruler appears at different distances, and therefore at different points in cosmic history, you can map out how space has expanded and curved across billions of years, not just at one single ancient moment. This is exactly what an instrument called DESI was built to do. The Dark Energy Spectroscopic Instrument, mounted on a telescope in Arizona, capable of measuring the precise distance and position of thousands of galaxies a night. Over the past several years, DESI has built up the largest three-dimensional map of the universe ever constructed, charting more than 14 million galaxies and quasars, some of that light having traveled toward us for over 11 billion years. Its first major results came out in 2024. A second, even larger release called Dr. 2 came out in 2025, drawing on 3 full years of observation. Pause on that number for a second. 14 million galaxies, individually measured, individually placed into a map of the cosmos so vast that earlier surveys, which once felt revolutionary, now look almost like rough sketches by comparison. When the DESI team used this enormous map to test the shape of the universe, on its own, without folding in the cosmic microwave background data we discussed earlier, something curious came back. Used by itself, DESI's baryon acoustic data showed a mild lean toward an open universe, omega minus 1 coming out slightly positive, around 0. 65, with an uncertainty wide enough, around plus or minus 0.7, that this result sits comfortably within the range of statistical noise. Not a discovery, not even on its own, something most cosmologists would call surprising. Astronomers are careful to stress that this remains consistent with a flat universe once you account for the uncertainty. But it's a thread, and thread by thread, this entire field tends to unravel old certainties. Here is the far larger thread, though the one that actually shook the field, and the one that brings the story of flatness crashing directly into a completely different mystery: dark energy. You likely already know, in broad strokes, that the universe isn't just expanding, it's accelerating, flying apart faster now than it was billions of years ago. A discovery that won a Nobel Prize back in 2011. For nearly 3 decades, cosmologists have modeled this acceleration using something called the cosmological constant, a fixed, unchanging amount of dark energy, baked permanently into the fabric of space itself, the same yesterday, today, and in 10 billion years. It's the lambda in the standard model of cosmology, called lambda CDM, the framework nearly every cosmologist has built their understanding of the universe around for a generation. Then DESI's data came in, and something in that framework started to creak. When cosmologists allowed dark energy strength to evolve over cosmic time, instead of holding it fixed and constant, the data preferred that evolving version, not by a small margin, but by a statistical significance climbing as high as 4 standard deviations in some combinations of datasets. When DESI's measurements were combined with supernova surveys and the cosmic microwave background, in plain language, dark energy might not be a constant feature of empty space at all. It might be changing, possibly weakening, as the universe ages. Astronomers estimate this remains short of the gold standard for an outright discovery, and the tension sits closer to 2 or 3 standard deviations once certain supernova datasets are swapped for others. So this is genuinely still unresolved, still being argued over in journals as we speak. But it was enough to make headlines across the world, with some outlets, only somewhat dramatically, asking whether dark energy itself might be dying. And here, very recently, is where this story folds back into everything we've spent the last half hour building. Because in 2025, a handful of independent research groups noticed something striking. If you take that same DESI data, and instead of letting dark energy evolve while holding the universe flat, you do the opposite. You let the universe have a tiny non-zero curvature. While holding dark energy fixed and constant the old simple way, the strange tension in the data substantially eases. One detailed analysis combining DESI's newest measurements with cosmic microwave background data and supernova surveys found a small but distinctly non-zero curvature, with omega minus 1 landing around 0.26, with an uncertainty of about 0.11, tiny, but intriguingly not quite 0. Let that settle for a moment, because it is genuinely one of the strangest plot twists in cosmology right now, and it has only emerged in papers from the last year. The signal that made headlines as evolving dark energy, the force that drives the universe apart, might be weakening, could instead be a sign that the universe has a faint, almost imperceptible curve to it after all, and that decades of assuming perfect flatness quietly baked a small error into every calculation since. 2 explanations, 1 set of data, and right now, nobody can tell you with confidence which one is real. Some cosmologists lean toward evolving dark energy. Others lean toward this whisper of curvature. Many, honestly, are simply waiting for more data, more galaxies, more years of observation before committing to either. This is not a minor academic squabble. The destiny of the entire universe hangs on the answer. If dark energy is constant, the universe expands forever, growing colder and emptier, galaxies drifting beyond each other's light until the night sky itself, eventually, goes dark. If dark energy is weakening, as some of this new data suggests, the long-term future changes. Perhaps the expansion eventually slows. Perhaps it doesn't, depending on exactly how that weakening behaves over time we haven't yet observed. And if it turns out that what we've been calling weakening dark energy is really just a sliver of spatial curvature we'd mistaken for something else, then the entire framework cosmologists have used for a generation needs a quiet fundamental correction. And the true fate of the universe may be written in geometry rather than in some exotic invisible energy field at all. We are living through this argument right now. Not a settled textbook chapter from decades ago, an active, unresolved disagreement playing out in research papers being written and debated this year, possibly even revised again by the time this video reaches you. That is something worth feeling for a moment. You are not hearing about an old mystery science already solved. You are hearing about the edge of what is known, the very edge, while it is still wet ink. So here's the question worth sitting with, the kind that might genuinely follow you into sleep tonight. If it turned out, a few years from now, that dark energy, the mysterious force scientists have spent 3 decades trying to explain, was never really a separate thing at all, but simply the universe revealing a tiny, hidden curve we'd been too coarse to notice until now. Would that feel like a bigger revelation to you than dark energy itself ever was? Would it feel like cosmology solving a problem, or like it quietly creating a stranger one in its place? Hold that question, because everything we've discussed so far, the cosmic microwave background, Planck's flatness measurement, DESI's 14 million galaxies, all of it describes only the patch of universe we can actually see. And it turns out that patch, as vast as it sounds, as overwhelming as 14 million galaxies may seem, might be an almost unfathomably small fraction of something even larger. We are about to leave the observable universe behind entirely and step into territory most people have never once been told actually exists. Let's start with a number that sounds almost like a typo the first time you hear it. The universe you can actually observe, every galaxy, every star, every last photon of light that has had time to reach us since the Big Bang, forms a sphere roughly 93 billion light years across. Not 93 billion years old. 93 billion light years in diameter, right now today, as you listen to this. That number is larger than you'd naively expect from an event that happened only 13.8 billion years ago. And the reason comes down to something we haven't mentioned yet. Space itself has been expanding the entire time that ancient light has been traveling toward us, stretching the distance between us and its source even as it traveled. So that the most distant light we can detect now comes from galaxies that after all this expansion sit far farther away than 13.8 billion light years. 93 billion light years. Sit with that for a moment, the way we asked you to sit with the wrinkled balloon a little earlier. If the orbit of Neptune around the Sun, already a journey light itself takes over 4 hours to complete, were shrunk down to the size of a single coin resting in your palm, the entire observable universe at that same scale would stretch out roughly the distance from New York to Los Angeles. That is the ratio we are dealing with. And every single measurement we've described tonight, Planck's cosmic microwave background result, DESI's 14 million galaxies, every decimal point of omega we've quoted, describes only what's inside that one coin-to-continent sphere, nothing more. Here is the sentence that should genuinely unsettle you, the one most people are never told. The word observable in observable universe isn't a casual qualifier. It is a hard, physical wall, built not from rock or energy, but from the simple fact that light has a speed limit, and the universe has only existed for a finite amount of time. There is more universe out there, almost certainly. Vastly more, sitting beyond a horizon we can never cross and can never even see past, not because our telescopes aren't good enough, and not because we haven't looked hard enough, but because the light from anything beyond that horizon has simply not had time in 13.8 billion years to reach us yet. It may never reach us. Depending on how the expansion of space continues to behave, some of that unseen universe may be retreating from us faster than its own light can ever close the gap. So when Planck's satellite measured flatness to within 0.2%, and when DESI's 14 million galaxies traced out a map consistent, more or less, with that same flatness, what they actually measured was the geometry of one single patch. A patch 93 billion light-years across. Yes, staggeringly large by any human measure, and yet we are now going to suggest to you, conceivably almost nothing at all compared to what may lie beyond it. This is where we return to that idea we asked you to hold onto earlier, the deflating balloon, stretched so violently during inflation that any wrinkles on its surface became invisible to a small observer standing on a small patch of it. We told you that inflation explains flatness not by making the universe flat, but by making it large enough that flatness is the only thing a small patch could ever detect. Now we need to push that idea one step further, into territory many physicists take seriously, even though it remains, by its very nature, untestable in any direct way. Some of the same physicists who helped build the theory of inflation, Andre Linde among them, and Alexander Vilenkin not long after, realized that inflation, once it starts, may not be a single, tidy event that happened once and then politely switched off everywhere at the same time. In certain versions of the theory, called eternal inflation, the inflating field doesn't stop uniformly. It stops in some regions while continuing in others, spinning off what physicists sometimes call bubble universes, each one a separate pocket of space where inflation ended, and a normal universe, like the one we live in, began to take shape. And crucially in this picture, inflation itself never fully ends. It continues forever somewhere, endlessly budding off new bubbles, each one potentially vast, each one potentially possessing its own physical constants, its own density, its own curvature, entirely independent of ours. We want to be careful here, because this is exactly the kind of idea that tips from real physics into speculation if handled carelessly, and we promised you honesty over hype tonight. Eternal inflation remains a hypothesis, a serious one, taken seriously by a meaningful portion of the theoretical physics community, but not something that has been observed, and arguably something that, by its very design, may never be directly observable, since any other bubble would sit, by definition, beyond our cosmic horizon, in the same unreachable darkness we just described a moment ago. Astronomers estimate cautiously that if eternal inflation is correct, our entire 93 billion light-year sphere, every galaxy DESI has ever charted, every photon Planck has ever measured, could be a single bubble among an uncountable, perhaps infinite number of others, each one its own universe. Each one, conceivably, flat or closed or open, independent of what we happen to find inside our own. And here is the part that should genuinely rearrange how you think about everything we measured earlier tonight. If this picture is even approximately correct, then asking, is the universe flat? May be a little like a single ant, standing on 1 square inch of an enormous, gently curving stadium roof, measuring the ground beneath its own 6 legs and reporting back, with complete sincerity and complete accuracy, that the world is flat. The ant isn't wrong exactly. It's simply too small, standing on too small a patch, to ever detect the curve of the thing it's actually standing on. We may be that ant. Our entire observable universe, 93 billion light-years across, awe-inspiring beyond almost anything the human mind can hold, may be the cosmic equivalent of 1 square inch of stadium roof. But that isn't the only strange twist hiding in the shape of space. Because even if we set aside everything beyond our horizon and ask only about the flat patch, we can actually measure there is still a second separate question nobody has fully closed the book on. Is that flat space infinite, or could it loop back on itself finite? Like a strange and enormous shape folding through dimensions we can't directly picture. This sounds contradictory at first. How can something be flat and finite at the same time? But it isn't mathematically. Picture for a moment the simplest possible example. A video game where you walk off the right edge of the screen and instantly reappear on the left edge, still walking in a perfectly straight line the entire time, never once feeling yourself turn or curve. That screen is flat. Every angle inside it still adds up exactly, the way Euclidean geometry says it should. And yet it is also finite, bounded, wrapping back on itself, a shape mathematicians call a torus, the same topology as the surface of a donut, just without any of the curving you'd associate with an actual donut surface. Flat geometry, finite size, both at once. If the universe were shaped this way, something remarkable would follow. Light from a single galaxy could, in principle, wrap around the entire universe and reach us again from a completely different direction in the sky, arriving twice, once directly, and once having circled all the way around. Astronomers actually went looking for exactly this signature, searching the cosmic microwave background for matching circles of temperature fluctuations appearing in 2 different parts of the sky. A search nicknamed fittingly, Circles in the Sky, led by researchers including Neil Cornish, David Spergel, and Glenn Starkman. First using WMAP data and later refined with Planck's far more sensitive measurements. If our universe wrapped around tightly enough, small enough, relative to that observable horizon, we should have seen these matching circles, clearly, unmistakably. We did not find them. Not in WMAP's data, and not in Planck's far more detailed maps either. This rules out a particular family of possibilities. The universe is almost certainly not small and wrapped, not folded up tightly enough that its edges sit within reach of our current instruments. Some of the most beautiful, almost poetic candidate shapes that were once seriously proposed, including something mathematicians call a Poincaré dodecahedral space, a 12-sided finite shape that some researchers floated as a possible explanation for unusual patterns Planck and WMAP both noticed in the large-scale structure of the cosmic microwave background, have been pushed to the edges of plausibility, if not ruled out outright by these searches. And this matters enormously. Ruling out a small, tightly wrapped universe is not the same as ruling out the idea entirely. If the universe wraps around, but does so on a scale even modestly larger than our observable horizon, light simply hasn't had time yet to complete the loop and come back to greet us. We would see no circles, no matching patterns, nothing, and the universe could still quietly be finite, wrapped, bounded, all while looking from the inside, exactly as infinite and flat as it does tonight. There is, as things currently stand, no way to rule this out. None. The question of whether the universe is finite or truly infinite remains, as honestly as we can put it to you, unanswered, and may remain unanswered for as long as humans exist to ask it. So here's the question we'd like you to actually sit with for a moment, eyes closed if you'd like, because this is the kind of thing that tends to feel different depending on which way your mind leans toward at night. Would you want to know with certainty if the universe wraps around on itself, so that traveling far enough in one single direction without ever turning, you would eventually circle all the way back and arrive again at your own starting point? Perhaps even glimpsing the ancient light of your own galaxy from the opposite side of the sky? Or would you rather it stayed exactly what it has always seemed to be, a true, endless, unbounded line, running outward forever, with no edge, no wraparound, and no way home? There's no right answer to that, but notice what's happened to the question we started with tonight. We began by asking simply whether the universe is flat or curved. And now, only a little while later, we are asking something far stranger, whether the universe is even one single, complete thing at all, or one bubble among countless others, finite or infinite, bounded or endless, in ways we may never have the instruments or the lifetime to settle. And there is one more layer underneath even that, a deeper unease than anything we've described so far. Because everything we've measured tonight, every omega, every flatness calculation assumes there is such a thing as the true fixed shape of the universe sitting out there, waiting patiently to be discovered. We're about to show you why even that assumption may not survive close scrutiny. Here's a question almost nobody asks, because it sounds at first like a trick rather than a real physical concern. When we say the universe is flat, flat compared to what? A ruler measures length against a fixed standard. A level measures flatness against the pull of gravity. What exactly are we measuring the universe's geometry against, when the universe is the only space there is, and there is no outside vantage point, no larger room to stand in from which to check our work? This is not a philosopher's idle wordplay. It cuts straight into something real about how general relativity actually works, and it's worth understanding clearly, because it changes what tonight's entire question even means. In Einstein's universe, geometry isn't a fixed backdrop that matter and energy simply sit inside, the way furniture sits inside a room whose walls were built long before the furniture arrived. Geometry and the contents of the universe are locked together, each one shaping the other, continuously, in real time. Matter tells space how to curve. Curved space tells matter how to move. There is no separate, independent shape sitting underneath all of it, waiting to be measured the way you might measure the fixed dimensions of an empty box before anything is placed inside. The shape is the relationship between the contents and the curvature. Change one, and you change the other. And here is the detail almost nobody is told clearly enough. That relationship has not stayed fixed across the history of the universe. The omega we've spent this entire video discussing, the ratio of actual density to critical density, has been evolving since the very first moment of the Big Bang, and it is still evolving right now, in this instant, as you listen. In the universe's early, radiation-dominated youth, omega sat balanced on that unstable pin we described earlier. A balance so precise it required tuning to dozens of decimal places, simply to still look this close to flat today. But as the universe has aged and dark energy, whatever it ultimately turns out to be, has come to dominate the overall energy budget of the cosmos, omega has begun drifting again, slowly, away from one, the unstable equilibrium finally beginning to lose its multi-billion-year grip. Far enough into the future, depending on which version of dark energy's behavior turns out to be correct, the universe's apparent geometry may shift in ways that would look genuinely different to an observer measuring it 100 billion years from now, compared to an observer measuring it tonight. In other words, flat right now may not mean flat forever. It may not even mean flat in some absolute, timeless sense at all. It may simply mean flat at this particular moment, in this particular 13.8 billion-year-old snapshot of an unfolding, evolving structure. The same way a single photograph of a wave, frozen at one instant, tells you almost nothing about whether that wave is rising, falling, or about to break. We have, in effect, taken one photograph of the universe's geometry, an extraordinarily precise photograph, built from satellites and instruments at the absolute edge of human engineering, and then asked that single photograph to answer a question about something that has never, in its entire history, stood still. This is where the dark energy mystery we described earlier folds back in, one final time, and it's worth saying plainly, this isn't a coincidence we're forcing together for effect. It's the same open question, viewed from two different angles. If dark energy is a true, fixed constant, Einstein's original cosmological constant, unchanging forever, then the universe's flatness, having survived this long, is likely to hold, drifting only imperceptibly slowly from here on, essentially locked in place for the practical span of anything we'd call the future. But if dark energy is evolving, weakening, behaving differently now than it did billions of years ago, the way DESI's recent data has hinted it might, then geometry itself is not a settled fact we're catching up to with better instruments. It is a still unfolding story, and the chapter we happen to be reading right now tonight is only one chapter among many. With earlier chapters we can still glimpse in ancient light, and later chapters that haven't been written yet. So the honest answer to tonight's title, "Why is the universe flat instead of curved?" may not be a single, clean fact waiting at the bottom of enough decimal places. It may be the wrong shape of question entirely. Not what is the universe's shape, as if shape were a fixed label sitting underneath everything, like a name on a map, but something closer to, what is the universe's geometry doing right now in this particular moment of its life, and where is that motion headed? A photograph, not a monument. A sentence in the middle of a much longer paragraph, not a verdict carved into stone. And underneath even that reframing sits the strangest fact of all, the one we asked you to hold onto a little while ago, back when we described the ant standing on its 1 square inch of stadium roof. We are not outside observers, calmly measuring a universe laid out before us like a map on a table. We are inside the thing we are trying to measure, Every photon Planck has ever collected, every galaxy DESI has ever charted, has reached us by traveling through the very geometry we're trying to determine, which means our measurement and the thing being measured are tangled together in a way a person studying, say, the shape of a coin from across a room never has to contend with. We cannot step back. We cannot get a wider view. We are using light that has already passed through the answer to ask the question. Maybe that's the real reframe tonight. Not that the universe turned out flat instead of curved, and not even that flatness itself might be temporary or local, or one bubble among countless others we'll never reach. The real reframe is this: the universe's geometry isn't a fact sitting passively out there, finished, waiting for us to catch up to it with better telescopes and cleaner data. It's a process, ongoing, unfinished, tangled irreducibly with the matter and energy and dark, mysterious forces moving through it. Forces we are, even this year, in papers being written and revised as we speak, still trying to understand. So here's the question to carry with you, quieter than the others, but maybe the one that lingers longest. If the shape of everything that exists is not a finished fact, but something still being written, still drifting, still being shaped by forces we don't yet fully understand, does that make you feel like a passenger riding inside something already complete, already decided, long before you arrived? Or does it make you feel instead like you happen to be conscious during one small, fleeting moment of something genuinely still in motion? Something none of us, not even the physicists writing these papers this year, can yet say how it ends. There is no need to answer that quickly. Let it sit, the way the best questions tonight have sat with you, unhurried, the way you might lie in the dark turning an old thought over slowly, not because you need to solve it before sleep, but because some questions are better held than answered. And it's with that thought that we're ready to step back, all the way out, and look at everything we've walked through tonight, one final time from a quieter distance. Let's go back, one last time, to the very beginning of tonight's journey, because it's worth seeing the whole shape of where we've traveled, now that we're standing at the far end of it. We started with a picture you've carried since you were small, flat space, stretching out like graph paper, infinite and uncomplicated, handed to you before you ever had the chance to ask whether it was true. We took that picture apart gently and showed you that flat is only one of three possible shapes the universe could have taken, sitting alongside a sphere curving back on itself, and a saddle opening forever outward, and that nothing in the raw physics of an expanding cosmos demanded we land on the flat one. We showed you the number omega, sitting so close to 1 that it required tuning to nearly 60 decimal places in the universe's first sliver of a second, a precision so strange that physicists needed an entirely new theory, cosmic inflation, just to explain how something so improbable could have happened at all. We watched that explanation nearly close the case, and then watched the case reopen first, when Planck's data briefly hinted at a closed universe, and then again, far more recently, when DESI's 14 million galaxies turned up a tremor in the data that some cosmologists now think might be evolving dark energy, and others think might be the universe's true curvature, finally peeking out from behind a number we'd assumed for 30 years was simply zero. We stepped past our own horizon into the possibility that our entire observable universe, 93 billion light-years across, might be a single bubble among countless others, each with its own shape, its own fate, sealed off from us by nothing more dramatic than the finite speed of light and the finite age of everything. and we ended by pulling the rug out from under the question itself, suggesting that the shape of the universe may not be a fixed fact waiting patiently to be discovered, but a living, unfinished process, one we are reading in the middle of, not from the beginning and not anywhere near the end. That is the real shape of tonight's question, and maybe the real shape of most questions this large. Not a straight line from ignorance to answer. A spiral circling back on itself again and again, each pass a little closer to something true, never quite arriving, never quite finished. And here at the close is where we have to let the original question go. Gently, the way you'd set down something you've been holding too tightly. We asked at the start why the universe is flat instead of curved, as though flat and curved were two final destinations, and the universe simply chose one of them and stopped. But you now know that isn't quite right. Flat, as best as we can tell, is not a destination at all. It's a description of where we happen to be standing on a patch of something larger that we may never see the edges of at a moment in cosmic history that is still actively unfolding. Measured by instruments built by creatures who have existed for the barest flicker of the time involved. Above was never a real direction in space, and in the same way, the shape of the universe, spoken as if it were a single permanent fact, may never have been quite the right way to ask the question. The universe doesn't have a shape the way a coin has a shape, finished and waiting to be described. It has a geometry, alive, tangled with matter and energy and dark, half-understood forces, still being written in real time, and we are reading only the page in front of us. What does that leave you with then, lying here, having followed all of this into the deepest hours of the night? Not smallness, we hope. Not the kind of dizzying insignificance some people feel when they're handed numbers this large. Something else instead, something closer to gratitude, strange as that might sound. You are a conscious noticing thing made of atoms forged in stars that died long before the Earth existed, standing on one small curved world, inside one small flat patch of a possibly endless structure awake. Right now asking a question almost nothing else in the observable universe is capable of asking. The universe does not know it is being measured. It does not know its own geometry is still being argued over in papers being written this very year. But you know. You specifically tonight, choosing to spend this quiet hour wondering about the actual shape of everything that exists, that is not a small thing. That is, as far as anyone can tell, one of the rarest things the universe has ever managed to produce. Before we close, if tonight's journey gave you even a few moments of that feeling, the quiet, specific wonder of realizing you live inside an unanswered question, a like or a subscribe genuinely helps this kind of slow, careful exploration find its way to more people who might need exactly this. Late at night the way you found it tonight, it costs you almost nothing. It means quite a lot on this end. So let the question rest now, unfinished, the way it deserves to be, somewhere above you, beyond the ceiling, beyond the atmosphere. Beyond even the most distant galaxy, any telescope has ever caught a glimpse of space is still doing whatever it is space does. Flat for now as far as we can tell, balanced on an edge so fine it shouldn't exist, drifting slowly toward an answer none of us will live to read. You don't need to solve it tonight. You don't need to solve it ever. You only need to notice that you're standing inside it, breathing here for this one brief, improbable moment. Sleep well under whatever shape the sky turns out to be. Good night.